Hey everyone, in this video we're going to be looking at an activity about joining or combining tables of data with dplyr. So to start, first thing like usual, we're going to load some necessary packages for this activity here. We'll go ahead and copy this code, get a blank new R Markdown document opened up, and then we'll paste this in here. We knit this. All right. So here's our R packages we're going to use. Okay. So specifically in this activity, what we're going to be looking at is how we can join or combine multiple tables of data, and how combining or joining tables of data like that can create implicit or explicit missing values. So implicit missing values are, or I guess talking about explicit missing values first, explicit missing values are values in a data frame or a table of data that have NA or another symbol indicating a missing value in the table. So they're very clearly indicated that there's an actual missing value in that cell of the table. That's opposed to implicit missing values, where sometimes an entire row of the data set is missing, but there's no NA values indicating that. It's just that an entire row is actually missing. Those are harder to recognize, more difficult to see that those are there in a data set. So we'll talk about how each of these types of missing values can show up. So once we get our packages loaded, then we can move on to talking about the data set. So here, we're going to be looking at this data set on Michigan flights, so airlines in Michigan, just from the year 2021. So flights going out of all airports out of Michigan in 2021. So this set of data that we're going to be looking at consists of multiple tables of data, all of which are interconnected or related to one another. So this set of related data tables is what we call relational data. You may have heard of a relational database that involves storage of multiple tables of related data. So that's why it's called relational data. So this data is from the AnyFlights R package and has different variables on the airport the flight was taking off out of, different time variables like the hour, the year, the day, the month of the flight, different weather variables, okay, all kinds of measurements about different flights and the airports and the weather. So first thing we're going to do is download this data file and import it into R. So if you click here, we can download this file. And then we will upload this file that we just downloaded to RStudio Workbench, or you won't need to do this if you're working in RStudio on your own local desktop or computer. But for RStudio Workbench, we will. So we'll click Files, Upload, choose File, and then navigate to where that downloaded file is located. Again, this is only for RStudio Workbench users. And so we find that file, click Open. Okay. All right. And then once it's finished uploading, we should see right here in our files pane that the file is here now. So this is a .rds file, which is a R-specific file type. So we can import this once you see it in the file viewer over here. You may need to navigate to it if you don't see it directly over here. Otherwise, one way to import it is to click it directly. Okay. So if you click on the file and then click OK, it allows you to import this into R in sort of a quick, concise fashion there. So we can copy that code that was run into the console and then take advantage of that, paste that into our Word document. Okay. So we're going to call this data set Michigan flights. So we'll change the name that RStudio picked automatically based on the name of the file. We'll change that to this. Okay. And note, you may need to update your file path depending on exactly where your file is located. So yeah, this part may need to be updated depending on your own machine or whether you're using RStudio Workbench or not. So once we get that imported into R, you should see the object over here in your global environment. Actually, oh, okay, it didn't run this properly. It called it something else. So we'll clear that out with the broom icon here and then rerun these chunks. Here we go. So that we have it called Michigan flights in our environment. Okay. Now we see Michigan flights is a large list. So it's a list type object with 5 elements. If we click on it, in the environments pane, we can see these 5 tables of data that are contained in this list called Michigan flights. Okay. So I clicked on it in the viewer here. That's one way. It automatically ran view Michigan flights, but we can also submit that code in a chunk. Okay. But we'll say eval equals false because we don't want that to compile every time to open up essentially this viewer every time we knit the document. I don't think it would hurt anything, but typically we would just want view to not be evaluated every time we knit a document. It's more just helpful to have in here. Okay. What type of object is Michigan flights? So it's a list. And what is its length? So it's a length 5. It has 5 tables of data in it. Airlines, airports, flights, planes, and weather. So these 5 data sets are how the data, when you scrape data about flights from the Any Flights R package, it gives the data to you in this format with 5 separate tables of data. One on the airlines, which describes the full name of each airline carrier along with its abbreviated code. A data set called airports that gives information about each airport identified by its FAA code. So that's like a short 3-letter code describing that airport. More detailed information about the flights. So this is the biggest data set and contains information about departure delays, arrival delays, the flight distance, the flight ID, things like that. Information about the planes themselves. So the actual machine that the passengers were on. This has information about the capacity of that plane, its engine type, other characteristics like that. And then lastly, a table of data that describes weather measurements at the different airports. And these are hourly measurements of the weather. So this graphic here showcases these 5 different data sets and how they're interconnected to one another. So talking about this graphic here, the flights data set is sort of the main data set, or the largest one, and this shows how all these other tables of data are connected to it. So for example, the planes data set is linked or connected to the flights data set via the tail num variable. So they both have a tail num variable that uniquely identifies each plane. So that's in the planes data set here. So there are almost 4,000 different planes in total in this data. And then there's about 150,000 flights. And that has the tail number of the plane that was on that flight. Okay, so that's how these two data sets connect. Airports, for example, connects via the FAA variable. So if we look at that, it connects to the flights data set via FAA. If we look at that, we can see here flights has this, let's see, origin column, which gives the FAA code. So DTWGRR. And if we look at the airports data set, that has, it calls it, this variable is called FAA, but it's the same as the origin variable. So that's how these two data sets are linked. So sometimes the variable, even though it's representing the same thing, sometimes the variables are not named the same exact way in each table of data, but that's still the variable that links the two. Okay. So these examples of the variables that link the two tables, tailnum and FAA, are what we call keys. These variables are just referred to as keys. Sometimes tables are linked together with a single key or a single variable, like planes and flights and airports and flights. And other times, the data sets are linked to with multiple variables. The weather data set and flights data set, for example, connect via these 5 variables: year, month, day, hour, and origin. So you have to match all of those in order to align the rows with one another in each of these data sets. All right, so moving on from that discussion. So we're going to be working with combining different combinations of these tables of data in this activity. So the first thing we're going to do, just to make things a little bit easier moving forward, is we're going to copy this code exactly. And run this code here. Okay, so when we imported the data sets, to make it a little bit simpler, I stored it, or the data comes as a list here of 5 different tables of data. So for example, if we wanted to refer to the airlines data set, we would have to use this syntax here. That would give us that table of data. And if we wanted the flights data set, or let's say the plane, planes, yeah. If we wanted the planes data set, we would use that syntax. Okay. But to avoid having to use this syntax every time we want to refer to these data sets in this activity, if we run this code, it breaks out each of those data sets into its own R object and puts them in the global environment. Okay. So that's why it's called list to environment. All right, so just going to make it a little bit easier to work with here. All right. So let's use Skim and Glimpse to look at some of these tables of data just a little bit to get familiar with them. So we'll say exploratory data analysis. Okay. So let's run Glimpse on, let's say, the flights data, the weather data, and then maybe the airlines and airports data. So let's knit that and take a look at what that shows us here. Okay. So looking at the flights data set, here we can see there's about 150,000 rows, 19 variables or columns. We have a year, month, day variable that indicates when the flight occurred, which day. We also have the minute and hour in which the flight left or departed. We have the departure time. Okay, those are some of the variables we're working with there. The weather data set has the origin or where the flight left out of. Okay, so that matches here with the flights data set. It also has a year, month, day, and hour variable, just like the flights data set does as well. So this is how these tables are linked. Okay. And then it has measurements about different weather characteristics. The airlines data set's much smaller, only 2 variables, 15 rows. It's the 15 different airline companies that operated in Michigan in 2019 that had departing flights out of Michigan. Yeah. And let's see. And then the airports data set gives information about the different airports that Michigan flights were departing from or going to. So you'll notice some of these are not Michigan airports. That's because flights left from Michigan leaving to land at those airports. So that's why these are included as well. This is described in the destination variable here in the flights data set, the destination airport. So that links with this FAA code again. This links with DEST, and FAA also links with origin. So these are some of the tables that we're working with here. Let's also use Skim to look at patterns of missingness potentially with the weather table. Let's look at that first. Okay, so when we look at the weather table, what we can see is that some variables have 100% of the values there and no missingness, like year, month, day, hour. Some of the other variables are more problematic. So temperature, dew point, and humidity, and the pressure variable all only had 1% of values that were non-missing. So that's really poor. That's a very large amount of missingness. Realistically, it would be very difficult to use those in any type of graphical display or model, since there's so many missing values. It's not reasonable to assume those measurements that are included are representative of our data set. So very likely we cannot use those variables here. But all is not lost. So we do have, again, many variables that are complete. So the wind direction and wind speed, wind gust speed, amount of precipitation. Well, precipitation is also very missing, only 4% of values there. But the wind speeds, those are nearly 100%. There are still a decent number of missing values, but certainly high enough that we could use these in visualizations or analyses. Okay. Also visibility, nearly 100% complete. 99 missing values is all. So that gives us some idea of missingness in the weather table. There's a lot of missing values, so we'll have to keep that in mind moving forward. Let's look at like the flights data set as well. And then that's the only one we'll look at for skim after weather. Okay. So the flights data set also has some missingness, but honestly, everything is either 100% there or close to it. So missing values aren't too much of a concern here. It would still be good to investigate patterns about which flights had missing departure times or missing arrival times. What's consistent about those flights? Maybe it's a particular carrier, a particular destination that has those missing values more often than others. That would be something that's good to look into. For now, since most of these values are here, we'll just proceed with combining, working on combining some of these tables and leave that for another day. Okay. So again, for these questions, this graphic sort of best shows how some of these variables connect, but also, so for example, the flights and planes data sets, if we look at the data sets in our environment, we have the flights table and then the planes table. So for planes, tail num is what connects planes with the flights data set. Flights and airports data set. Okay, what about the flights and the airports? So we already mentioned this actually. It's the FAA code, right? That's what connects to flights via two variables actually, the origin and destination variables. And for flights and weather, those connect through a lot of variables. So the year, month, day, and hour, and origin variables. The weather is hourly. So if we specify the year, month, day, hour, and origin, the airport the weather was occurring at, that is sufficient to link the two tables. All right. So now suppose, hypothetically, we wanted to draw a map showing the route each plane flew from its origin to its destination. Let's think about which variables we would need and which tables we would need to combine. So let's think about if we were plotting this on a map, maybe a helpful thing to think about is what are the two axes on a map? What is the X and Y variables when plotting on a map? And then do any of the tables have that information? Okay, so if we want to plot where each plane is flying, we need its origin and we need its destination to be able to plot that on the map. The flights data set alone will tell us the name of the origin airport and the name of the destination airport, but we couldn't plot this on a map because we don't know exactly where DTW is, the Detroit airport. We don't know exactly where the Phoenix airport is. I mean, we could Google it, but if we actually wanted to have R create a map, we need to give it very specific coordinates. So that's where we can, if we connected this with the airports data set via the FAA variable, then we would have not only a longer name of the airport, but importantly, we would have the latitude and longitude, which would essentially provide us with the longitude and latitude would provide us with the X and Y coordinates respectively for plotting this on a map. And assuming a straight line sort of route from one point to the destination, from the origin to the destination, we could then draw a line showcasing that approximate route of that flight. Okay. So we would need the FAA variable, the lat variable, the lond variable, and the origin and dest variables in order to plot approximate routes of every flight. Now, suppose we wanted to learn more about weather patterns for departures, for flight departures, okay, and how that relates to departure delays. Specifically, if we're only looking at wind speeds and precipitation, which variables would we need for this, and which tables would be required? So looking at departure delays, the flights data set is the one that has the departure delays information. If we wanted to relate via modeling potentially the departure delays with different weather characteristics, we would need to combine the flights data set with the weather data set. And we would need the year, origin, month, day, hour columns in order to join those two data sets together. Those are our key variables. And then we would want the wind direction, wind speed, and wind gusts to describe wind. Oh, and for precipitation, the precip variable. You'll notice that with the precipitation, just sort of looking at it here, might be able to notice a trend about all the non-missing values. Well, they're quite small. We sort it. And I guess some are zeros. But a lot of the missing values could potentially be missing just because they're zero. There actually was no precipitation, although we can't know for sure. So I guess we should not assume. Okay. So moving on from those points, we'll talk about different methods for combining or joining tables of data. So the three most common types of methods for joining data tables are what we call left joins, in which we keep, so when joining two tables X and Y, left joins are when we keep all observations in X, the table on the left, but not necessarily all observations in Y, the table on the right. Right joins are analogous to left joins, but with the data sets switched about which one we're keeping. So keeping all the observations from. So with right joins, we keep all the observations in Y, but not necessarily in X. And then a full join, which is the most common type of data join I do because it retains the most information about both data sets, keeps all observations in both X and Y. So note that these three types of joins are all specific types of what are called outer joins, and that they can create what are called explicit missing values, meaning that NA values can be generated as a result of these joins. And this is this concept of joins is agnostic to the R programming language. We'll look at how we can do left joins or right joins or full joins in R, but these are types of data combinations, joining of tables that is done in other languages as well, like SQL, SAS, and Python. So explicit values, if you want to read more about those, that's in chapter 19 of R4DS. But here's some graphics showcasing what goes on in those types of joins. So a left join here again, we have this key variable that has values 1, 2, and 3. And this is X. And then we have the Y table that has a missing value and values 1, 2, and 4. So notice that 1 and 2 have matches for the key variable in both data sets. So those align together nicely. Those are concatenated. And then because this is a left join, we keep all the rows in X. But if there's no matching value for the key in Y, that row is dropped. So Y3 was dropped here. Similarly for a right join, 4, 1, 2, and 4 are in Y, so those are kept no matter what, with 1 and 2 having matches. 4 didn't have a match, but it's a right join, so it's kept. And then X3 here, this row is dropped in X because it's a right join. Okay. Lastly, for a full join, we have values 1, 2, 3, 1, 2, and 4. All of these are kept, merged where possible, and where there's not matches, so for 3 and 4, there's NA values in each corresponding spot. So this is how these types of joins can create explicit missing values, NAs that actually will show up in the data table. So let's try out some of these types of merges or joins with the airlines data sets here, with all these different data tables. So combine the flights and airlines data frames with left join. Let's do this first bullet. Combine the flights and airlines data frames. Okay, so we do flights, we do flights, pipe, left underscore join, airlines, to create a new data set called flights carriers. If we run this code, we can see flights carriers has about 150,000 rows. Note that it has exactly the same number of rows as flights. And in fact, the variables are going to look very similar. The last variable of flights was time hour, but flights carriers, the last variable is now the name of the airline carrier, which was inherited or came from the airlines data set. This name variable. And see how the key was the carrier column. So when we ran that code, dplyr gives you a little message that says joining by carrier. It's letting you know it automatically found 2 matching variables in each of the data sets, and so it merges by those. So this is a really nice feature of left join in that it automatically finds matching column names in each of the 2 tables you're trying to join, and will join them based on that matching or those matching variables. So we can explicitly, sometimes they're not named exactly the same in each data set. In this case, it was, so it worked nicely. But when they're not, or if you want to be more explicit, you can list out the keys for each data set in this by argument. So the syntax is by equals, and then we do a vector, and we do key variable in the left table equals the key variable in the right table. So again, in this case, flights had a variable called carrier that was the key, and then airlines had a variable called carrier that was also the key. So it happens to be the same here. This code functions exactly the same as the code we already ran before, but it's more explicit. And notice we don't get the message anymore since we manually specified the merging variable, the key. So now using this data set, we can calculate the average flight distance for each carrier. So let's think about that. Which dplyr function or functions would we use to get the average distance for each carrier? So we can use group by and summarize. So what are we grouping by here? We're grouping by the carrier. And then what are we summarizing? Well, we want the average flights for each carrier. So let's call it AVG distance. And if we look at this data set, there is a distance variable. It's not in here. So if we look up here, there's a distance variable right here. It gives the flight distance in miles. So average distance equals mean distance, comma, na.rm for na remove equals true. Because we want the mean calculation to exclude missing values. Otherwise, it just shows up as a missing value. Okay, so if we run that, here this gives us the average flight distance for each carrier. And then maybe to make it easier to see what's the largest and smallest average, we can sort this data set using a range. Okay. So now we can see that the carrier, let's see. But you know what? To get a better idea of which carrier that is referring to, let's do carrier underscore name, because that variable in the data set, like carriers. Or what is it? Oh, name. Yeah, let's actually do it by name. This variable here, because it gives the full name of the airline. So it's a little bit easier to see who that is. Yeah, so let's run that instead. Okay, there we go. Now it's a little bit easier to see who that is. So Endeavor Air had the shortest flights on average. And then if we arrow over here, Alaska Airlines had the longest flights on average at almost 2,000 miles. So very far, but that checks, that's in line with the fact that Alaska typically flies out to Alaska or Seattle, very far away places from Michigan. Okay. Now we will combine the weather and flights data sets. Okay, so let's maybe do this in a new chunk. Create weather flights. We'll do left underscore join flights. How many rows does weather flights have? So if you look, it automatically joined by origin, year, month, day, hour, and time hour. Okay. So I noticed when I was looking through these data tables that there's a mistake in how the weather data comes when you scrape it from the any flights package when it's given to us here. So we're actually going to only going to merge by some of these variables. So we're going to exclude time underscore hour. Okay. And we're only going to merge by these variables. So origin equals origin, because these are named the same in each data set. Again, we can do this. Okay. Okay. We run this. That works. Okay, so the reason we were not merging by the time underscore hour variable as well, if we look at the weather data set, I'll show you this issue that I found with it. So notice that the year has 2021, month, day, hour. Okay. So this is saying the 0th hour on the first day of the first month of 2021. And these variables line up and match with the flights data set, which also has year, month, day, and an hour variable. Notice how in the flights data set, we have 2021, 1, 1, so January 1st, 2021, and then hour 5, the time hour variable aligns with that. 5 hour, it's hour 5, 6, and then 6 here, and so on. This is all consistent and correct in the flights data set. This is not the case in the weather data set, which took me a while to figure out what was causing issues. So here, if you look at the hour variable, it looks like it's shifted by 5 hours for some of the rows. So this is inconvenient. And the issue is that it won't find that the data sets match up anywhere when it tries to merge on time hour. So we exclude that variable when merging them. And we'll just do it based on these variables instead, because these correctly specify the weather times. I'm not sure why they had an issue in the data, how that was recorded, but there was some issue in the weather data set. So we will manually work around it here. Okay, so how many rows does this data set have? Well, we could look over here in the global environment, weather flights. It has 168,159, about 168,000 rows, or we can, let's have R do it for us. So it'll print the number of rows here using nrow. Now let's combine the flights and weather data in that order. So let's copy this code and then update it to switch the order of weather and flights. And we'll call it flights weather Make sure to get rid of the period there. And let's see how many variables, how many observations this has. $149,445. Okay. So flights weather, 149,445. That's the same as the number of rows in the flights data set, which makes sense because it is a left join. And there were more right. It's how it worked out with this data set based on the number of flights that had non-missing weather information. So now we'll look at doing a full join with the weather and flights tables. Okay. So a full join is agnostic to whether you do X or Y first. So the order of the two tables does not matter for full joins. So we'll just copy the same code again from the previous part, and then we'll change it from a left join to a full join. And we run this. Okay. How many rows does that have? So that has 168,505. So this has the most rows. So this will always be the case that a full join of two data tables will have the same number of rows or more than a left join of two data tables. Because the left join is guaranteeing keeping all the rows in the left table and potentially only a subset or all of the rows on the right side table. But a full join always keeps all rows from both tables, so it maximizes the number of rows retained. But when we did all of these merges, there was a lot of explicit missing values that were generated. Okay. Considering all the data we have available, how many flights have missing wind speeds? Okay. So we could use a skim to find this out, or we can manually sum up the number of missing values ourselves. But let's think about which of these three tables, weather flights, flights weather, weather flights full, which of these would tell us how many flights have missing wind speeds? Okay. There's a few ways to get at the answer. There's not one unique way. So one way we could do this is to look at the, let's see. If we want to find the number of flights with missing wind speeds, okay. One way we can do this is to use the dataset flights weather, because this kept all the rows in flights and essentially appended it with weather information when possible. So this has every flight. Each row corresponds to a single flight. And if there's a missing wind speed, that flight does not have a measurement for wind. Okay, so this is the data set that we want to use. The full join will have some extra rows, because if we look at the full join here, okay, at first, I guess I'll show the number of missing values for each of these. So let's look at flights weather. So if we go flights weather, we can use this function from dplyr called pull that manually extracts a column from the data set. So we're going to pull the wind speed column. Oops. Okay, and what this looks like is it'll pull out the raw values of that column. So all the numbers here. With those numbers, then we pipe that into the is.na function. So that checks if each value is missing or not. And so now it'll turn those all into trues or falses, depending on if they're missing or not. And then we can take advantage of the fact that false values in R are equivalent to zeros, and trues are equivalent to the value of 1. So for example, if we sum false, true, true, false, false, that'll give us the value of 2. This will count the number of trues in a Boolean vector like this. So we can do that here as well. And we get 1526. So there was 1,526 missing wind speeds for flights. Or in other words, 1,526 flights had missing wind speeds. If we tried this with the full flights data set, this wouldn't give us the right answer, but we'll talk about what this shows us. These will give us different numbers. 1849. But which one is correct? It's this one. Okay, if we look at the weather flights full, we look at wind speed. Okay, we can sort to where, if we scroll to the bottom, after sorting, here's all the missing values. And now, what you can see is that there's no wind speed information, but there's also no flight information. This is just weather information here. It gives the airport the weather was located at, the hour, the time, but there's nothing about a flight. There's actually no flight. So this includes some extra rows where there's no flight info and no weather info. No wind info, I should say. Okay. Why was that included? Well, it looks like there was still some visibility measurements that were taken. So that's why these were still included in the weather data set. But that's why we want to be careful about which tables we're joining with which ones if we want to measure particular things. So in this case, the full data set is not actually what we wanted. This gives us the correct answer here. So now that was talking about outer joins. Let's talk about inner joins here a bit. So inner joins only retains rows between the two data sets where there were matching key values. So for example, if the key variable here had values 1, 2, and 3, and then in the second table, y had 1, 2, and 4, since 1 and 2 are the only matches, that's all that's retained in an inner join. This creates what's referred to as implicit missing values. In the resulting table, we no longer have any NAs. There's no missing values in the cells of the table, but there are rows that were dropped or that are missing now. This row with the value of 3 and this row with the value of 4. They just no longer are in the table, but they technically are still missing values. So these are harder to spot. Like skim won't show that to us. using the sum trick with is.na won't show us that these missing values are there. So this is something that we have to find upon manual inspection or some clever manipulating of the data sets. Okay. These are always important. Implicit missing values are always important considerations in the data. So first, let's combine the weather and flights data frames with an inner join to create a new data set called inner weather flights. And this, just like the full join, is agnostic to the order of the variables, the order of the two tables. It doesn't matter which way you put them for an inner join. Okay. We'll create this data set. Okay. And then see how many rows it has. So we think this will have more or less rows than the whole weather flights full. It's very likely going to have less. Oops, yeah, we have to specify, because of that issue with the time hour, we have to specify the by variables. Okay, so also as another trick when you're combining tables with these join functions, if the variables are named the same way in each of the data sets, like they are here. Okay, so we have like year equals year, month equals month. Those are the same in both tables. You can actually just list them out once without the equals in a vector like this, and that works as well for merging. So this is equivalent to this by argument. This by argument is equal to that in terms of the join functions. So we'll do it like this. So make sure to exclude time underscore hour. Okay. And then we get 149,100. So we have less, some rows were lost from the flights data set, but not too bad. Okay. So that means that there were some rows that didn't match up in terms of origin year, month, day, and hour between the two data sets. So about 345 rows were dropped from flights. Okay. What does that tell us about? So, right, so since inner weather flights had less rows, let's see, weather flights. Right, since it had many less rows than weather flights, what this tells us is that since inner weather flights had 149,100 rows, whereas weather flights, if we look at that, weather flights had 168,000 rows. That means that some airports had hourly weather data, but no flights departing during that hour. Okay. So I'll type that out. This means that some airports had hourly weather data but no flights departing during some hours. Okay, and this seems totally realistic. Maybe they have stations set up at the airports that are constantly measuring weather variables, but it's not necessarily the case that there's always a flight going out every single hour, especially at smaller airports. Maybe they don't always have flights going out every single hour. Okay. Like Lansing, the Lansing airport, for example, in this data set is very small. So that's the last part of this activity. Then here's this useful little graphic as well that showcases graphically how you could represent an inner join, essentially only keeping the intersection of two tables, where each circle is a table here. Left join, full join, and right join. Okay. I found these very helpful in describing the different types of joins. And then you can read more about relational data, again, in the R4DS book, the R for Data Science book. So that's it for this activity. Thanks.